I continue to talk a little bit about change of state, in particular evaporation. Hopefully you had a chance to watch the video where I boiled water in a paper cup. So if you didn't, go back into Google Classroom and find that video where I boiled water in a paper cup. The cup never burned. However, the water inside of it was boiling vigorously, even though I had a Bunsen burner right beneath that cup. So all of the heat from the Bunsen burner was going into change phase, taking the liquid phase to the gaseous phase, and the temperature never increased beyond the boiling point. So make sure you go back and watch that video if you haven't already. Now, continuing to talk about evaporation. Remember the little girl who jumped in the swimming pool, and when she got out, she was shivering. And we said that the reason she was shivering was because it was an endothermic process to change water from its liquid to its gaseous phase. And that energy came from that person's body. It came from the surroundings. Well, what happens if the opposite happens? What happens instead of particles leaving the surface? Isn't it possible that they could come back to the surface and condense? So it is possible for gaseous particles that have evaporated to collide with the surface that it left, if its kinetic energy is low enough at the time of the collision. The particles may again become part of the liquid. Now, that would be an exothermic process, and that would actually add heat to the surroundings, which would be the little girl, and she would actually warm up. But she doesn't. She shivers. Why? Well, because we're considering the girl to be an open container, so to speak. In other words, it's highly unlikely that a water molecule, once it's left the surface of her body, that it's going to come back. It's going to leave and fill up the surroundings, the area, the world for that matter. However, if this happens in a closed container, the chance of this type of collision increases. In fact, we reach a point where just as many molecules of gas return as leave the surface of a liquid. In a closed container, the rate at which molecules evaporate equals the rate at which molecules condense. In other words, the liquid is turning into a gas, but at the same rate, the gas is turning back into a liquid. And so the volume of liquid in my container is not going to change. Take a look at this image here. If I put a dome over top of a container of water, initially, since there are no water molecules underneath that dome yet, molecules will be leaving the surface and starting to fill up the container. They'll be bouncing off the walls of the container. They're trapped. Won't some of those have the opportunity to come back and become part of the surface of the liquid again? And so we're going to reach a point where the liquid volume remains constant. And that's when the rate of evaporation, so going in this direction, is equal to the rate of condensation going in this direction. And we say that's an equilibrium condition. That's a neat word, isn't it? It's a special kind of equilibrium condition called dynamic equilibrium. And we talk a lot more about equilibrium later this trimester. So for now, just understand the term equilibrium. It's the rate at which something's happening in one direction equals the rate of that happening in the opposite direction. And that's called an equilibrium condition. All right, let's talk now about boiling point. Boiling point is interesting. It involves the fact that bubbles of water vapor from anywhere in the liquid can rise to the surface. Think about how that's different than evaporation. That's right, you remembered. Evaporation, the particles have to have enough energy, but they have to be on the surface. For boiling to happen, that vapor phase can occur anywhere in the liquid. This only occurs if the vapor pressure of the liquid is equal to something that we call atmospheric pressure. Now at sea level, atmospheric pressure is what we call 760 millimeters of mercury. Oftentimes it's referred to as 1 atmosphere. Now here in Idaho Falls, where we're about 45 or 4,600 feet above sea level, the atmospheric pressure is considerably lower, actually. It's about 640 to 645 millimeters of mercury. And that's simply because there's less air above us. The amount of air above us here at 4,500 feet above sea level is less than the air that's above us if we went to sea level. So the atmospheric pressure at sea level is much higher than it is here in Idaho Falls. Now that will actually affect the boiling point of a liquid. Let's read what boiling point is. It occurs when the vapor pressure of the liquid is equal to the atmospheric pressure. Now what is vapor pressure of the liquid? Well, if you remember a few minutes ago, or in the last lesson, we had a beaker of water and we put a little dome over it. And we set it on our tabletop. And didn't some particles leave the surface and enter the gas phase? And they started saturating this with water vapor. And then some of the particles eventually return to come back to the surface of the liquid. Nevertheless, aren't there always going to be gas particles inside that dome now? Well, aren't those gas particles moving around and colliding with each other and hitting the walls of their container? They're moving all over the place in there, and they're exerting a force. We call that force caused by the water vapor inside there water vapor pressure. And that's dependent upon temperature. So it depends on the temperature. I mean, think about this. As I warm my container up, aren't more particles going to leave? And the particles that I've left, aren't they going to be slamming into each other in the walls of their container with more force? So they get more and more energy as we heat them up, and so the vapor pressure increases. So vapor pressure increases with the temperature. Well, it turns out if that vapor pressure gets high enough, it can actually equal atmospheric pressure. So let's say we're at sea level. If I heat my water up over here high enough, the vapor pressure of the water vapor molecules becomes equal to the vapor pressure, the atmospheric pressure, and boiling will begin. So boiling occurs when the vapor pressure of the liquid is equal to the atmospheric pressure. So you have to get it hot enough so the vapor pressure of the liquid equals whatever the vapor pressure is of the atmosphere around it. Now remember, in Idaho Falls, the vapor pressure is lower than it is at sea level. So do we have to get it as hot here in Idaho Falls? We don't. In Idaho Falls, water will boil at about 98 degrees Celsius, where at sea level, water boils at 100 degrees Celsius. That's because we don't need as much energy for the vapor pressure of the liquid to equal the atmospheric pressure. So it is possible for water to boil at temperatures less than 100 degrees. If we were in Salt Lake City, where the atmospheric pressure is pretty similar to what it is here in Idaho Falls, water will boil at about 98 degrees Celsius. Now, I think this is interesting here. It's possible for water to boil at temperatures higher than 100 degrees Celsius if the pressure above the water is in excess of 760 millimeters of mercury. A greater amount of energy is required for the molecules to push each other apart. So if the atmospheric pressure is higher than 760, we have to add more heat before the water begins to boil. So think about Instapots. Maybe at your home you might have an Instapot. And an Instapot uses this concept to its advantage because the atmospheric pressure, the pressure inside that pot, is increasing because it's sealed and those gas particles have nowhere to go. So the pressure inside that pot increases. Thus, it takes more energy for the water to boil. So in an Instant Pot, the water, instead of boiling at 98 degrees Celsius, where it would on a pot sitting on your stove, might boil at temperatures higher than 100 degrees Celsius. It could get in excess of 110 degrees Celsius. Well, think about your food. Isn't it going to cook faster when it's 10 or more degrees hotter inside that Instant Pot? Absolutely. All right, so it also would follow that at lower elevations, higher elevations, the atmospheric pressure will be lower. So at sea level, water boils at 100 degrees Celsius. On the top of Pikes Peak in Colorado, which is 4,400 meters above sea level, so the atmospheric pressure is considerably lower, it doesn't take as much energy for the water to boil. So it can boil at 85 degrees Celsius. In fact, on top of Mount Everest, the altitude is 8,800 meters above sea level. Water only needs to get up to 71 degrees Celsius. So as elevation increases, atmospheric pressure decreases, and the boiling point is lower. Now, I want you guys to watch a video of me boiling water at room temperature. Now, in order for water to boil at room temperature is about 20 to 25 degrees Celsius. Think about what the atmospheric pressure would need to be. The atmospheric pressure would be very low. And you'll see how I do that in the video, and we can get water to boil at room temperature. Now people are going to say, well, man, that's got to be hot. It's boiling water. No, 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 no. I'm holding it in my hand actually when it happens, and it's only about 20 to 25 degrees Celsius. So think about that as you watch the video. All right, that's good enough for today. We'll talk to you soon. Bye-bye.